This lecture is called Coulomb's Law, Interacting Charges, and the question we're going to investigate together is how do the subatomic particles within the atom interact? So last time we met, we talked about the fact that atoms have a nucleus in their center that's positively charged and that has a lot of mass. We also said that most of the atom is empty space, but that electrons are small particles with basically no mass that exist outside the nucleus. So the question is, how does this negative charge on the electron interact with this positive charge in the nucleus? How do electrons, negative and negative, interact? So we're going to explore this with a simulation. So I'm going to do a series of experiments with these two charges, the red charge here and the blue charge here. And after we explore how the forces of attraction or repulsion change, then we're going to try to write a mathematical rule or a mathematical formula that shows the relationship between forces of attraction and repulsion with different variables. So the first thing I want you to note, this charge right here is a +1, okay? So it's like a proton in an atom. This charge right here, the blue one, is a -1, so it's like an electron. And these arrows, the arrow that's pointing toward the red and toward the blue, these are showing the force between the red and the blue charge. Because the charges are pointed toward one another, what that means is that when this charge, this blue charge, gets closer to this red charge, there's going to be a pull, almost like how two magnets attract. There's going to be a pull between the red and the blue charge. Okay, so one is positively charged, one is negatively charged, and when charges are opposite like that, they attract. Now, I could look and say, what happened if I had a +1 and a +1? So I'm going to change my blue charge to be a +1. Okay, now look at what happens. Positive and positive, when they're put together, the force of the force points the opposite way. Notice this force is pointing away from this red, and this force is pointing away from this red. So if you were to put these two red charges together, you would feel a push away. They would not want to go together. They would repel each other. Okay, notice down here, we're now talking about a force of repulsion rather than a force of attraction. So I'm going to go back to a force of attraction. Okay, the blue charge -1 and the red charge are pulling toward each other. Now I want to see what happens when I pull these charges further apart. Is there going to be more attraction or less attraction? You can watch the size of the arrows to tell. So I'm pulling apart, look at those arrows. They're getting smaller and smaller. Okay, look at the number here. It was 6.6 and now it's 1.6. So as I pull charges apart, you can even think about if you were pulling magnets apart, the further away those magnets are from each other, the less attraction or repulsion they would feel. And that's the same with charges. If you put them close together, watch those arrows grow. Very large now, they're super close. And then those arrows of attraction get smaller as they're drawn further apart. Oh my goodness, I'm sorry. There's some kind of motorcycle race happening in my neighborhood. We will ignore it. Okay, and the last thing, so we've looked at opposite charges attract. The further apart they are, the less attraction there is. The last thing I want to explore is what happens when you change how big the charge is. I'm going to make this from a from a -1 to a -2. And I want you to watch the arrows. I'm going to make it bigger. -3, I guess I can't go any further than -3. But did you notice those arrows got a little bit bigger? And I can do the same with this positive charge. I can make it +2. Notice those arrows? +3. They got bigger each time. So the bigger the magnitude or the size of the charge, the more attraction that exists between two charged elements. Okay, and you could we could think about this being useful for us. Maybe we have a nucleus that has 3 protons, so it's +3, and an electron is -1. We want to be able to think about what's the interaction between that electron and those protons, because that's going to determine how atoms behave and ultimately help us explain the properties of elements. So let's summarize this by taking a series of notes. Oops. Okay. So we're gonna look, if you wanna copy these data tables into your notes, you can, or if you wanna just focus on drawing these pictures, you can. But I wanted to show each line represents a different experiment. So this first experiment would be if I took that red +1 and that blue -1, and I have them some distance apart, then this number over here is showing us the force of attraction. So you can see here positive and negative attract, and then negative and negative, whoops, I didn't fix this before I made it. These two should be pointing away from each other, just like this arrow and this arrow point away. Okay, and then notice that the sign on the charge changes. Because it's a -1 and a +1, you end up with a negative force of attraction. Anytime it's negative, that stands for attraction. And if you have a negative and a negative, or a positive and a positive, you're going to end up with a positive sign here, and that's going to represent repulsion. The main thing to take away from this slide is that if you have a plus and a minus, those opposite charges are going to attract each other. That's like a proton and an electron. But if you have like charges, say a minus and a minus, an electron coming close to an electron, they're going to push away from each other and they're going to repel. That would be true if you had a +1 and another +1. So 2 protons coming next to each other would also repel. Okay, this next set of data shows I've got a +1 and a -1. A +2 and a -2, and a +3 and a all -1s here. So charge 2 is staying the same. I'm not changing that variable. I'm going to keep them the same distance apart. I'm not changing that. And in each case, they're attracting because it's a plus and a minus. So the only thing I'm changing is the sign of charge 1. In this first example, in experiment 1, I have a plus, and in experiment 2, I have a +2. So I'm basically multiplying the charge times 2 here. And I want to ask, when I make the charge double what it was, what happens to the force of attraction? If you look, I know these numbers, they're kind of crazy. They're super small, and we haven't talked yet about scientific notation. So just focus on this number. 2.3, 4.6, okay? 2.3 times 2 would be 4.6. So as I double the charge, I double the force of attraction, okay? So if I'm comparing a +1 and a -1 versus a +2 and a -1, there's going to be more attraction between charges when the charge has a bigger magnitude. And that's the same here, right? If I increase to +3, I have an even bigger number here, 4.6 to 6.9. So our rule is, and I would take some notes on this, as charges increase in value or increase in magnitude, the force of attraction or the force of repulsion is also going to get bigger. It's going to increase. Okay, this is now an example of looking at charge 1 staying the same, charge 2 staying the same, but the distance now we're going to change. Okay, so let's look at what happens. When I put a +1 and a -1 here, a +1 and a -1 together, and they're, let's say, 100 picometers, that's just a really, really small distance. That's okay. 100 picometers apart, I have a force of attraction that's 2.3 times 10 to the minus 10. If I make these 3 times more spread out, right? 100 times 3 is 300. So 3 times more spread out, look what happens to the force of attraction. 2.3 to 0.26. It doesn't decrease by dividing by 3. It actually decreases by dividing by 9. So when I make the distance 3 times bigger, I'm making the attraction 9 times smaller. That's very significant. So here, if the charges are closer together, there's more attraction. If they're further apart, there's less attraction. So our rule, as distance increases, force of attraction decreases. So it's opposite. As the distance between the charges gets bigger, the force of attraction gets smaller. And I would keep magnets in your head as a mental model. When you pull a magnet away from the fridge, right, it very quickly loses its attraction for the refrigerator with even just a little bit of distance away. So distance plays a bigger role here. So I want to summarize those 2 rules that we just saw into a mathematical formula. So scientists have created a law called Coulomb's law to explain the observations we just looked at in terms of how charge and how distance affects force of attraction. And here's the formula. F stands for force of attraction or repulsion between 2 charges. Okay, so force is equal to the charge of the first particle times the charge of the second particle divided by the distance between those charges squared. Okay, what does that mean? Let's look at an example. So here was charge on the first particle. That would stand for Q1. So notice in parentheses, I put +1 for Q1. Here's the second charge. It's a -1. It's Q2. So down here, I put it in Q2 is -1. And the formula tells me you multiply Q1 times Q2. You're then going to divide by the distance between the charges squared. So I just made up a number here. Radius, or r, the distance between the 2 charges, is from the center of one charge to the center of another charge. I just assumed here it's 100 picometers, and I squared it because distance is squared. Now, let's say I wanted to compare, is the force of attraction between these 2 particles stronger or weaker than the force of attraction between these 2? Well, I could use this Coulomb's law formula. For Q1, this orangey guy, +2. So I'm putting in +2 here for Q1. Q2 is charge number 2. It's a -1 still, didn't change, -1 here. And then the radius, or the distance between these guys, also didn't change. It's still 100 picometers squared. So whenever you want to determine is an attraction between 2 charges greater or less than another, you could use what we call this Coulomb's law ratio to decide. So if you put in your calculator 1 times 1 divided by 100 squared, and then put in your calculator 2 times 1 divided by 100 squared, you would see that this is a bigger number, which means there's a greater force of attraction. Okay, so Coulomb's law is at the heart of everything in chemistry. Always we're asking ourselves, what's happening between electrons, the negative parts of atoms, and protons, the positive parts of atoms? And we can use these ideas of attraction and repulsion to explain most properties in chemistry. It's a really powerful tool for thinking about atoms and how they behave. Okay, so I'm going to stop this lecture here. Our next lecture is going to explore periodic trends, and then we're going to think about how forces of attraction and repulsion can explain them.